For the 12 volt power connections and high current loads, including those to the 24 volt scooter motors, although I'm only using 12 volts, I'm still using 24 volt hookup wire that you can get from electric car garage opener wiring. I recycled some from my electric garage door, but you can buy those again at the hardware store. They're solid copper, 24 volt, and they're also used for alarm systems. Very nice wiring. Even though it's solid, it's pretty flexible and very rugged and can handle the large current loads needed to drive the motors. Tying them all together, I use the standard house wiring twist-on caps with electrical tape and then coat it with black liquid tape. These can usually handle loads of up to 120 or 240 volts. They're used for safely wiring your houses, including your lighting systems and stoves and other appliances. You can tie like multiple wires together, and that's how I form the circuits for the relay and the 12 volt power circuits that can power the motors using the HB25 motor controllers. From the 12 volt SLA battery, you see the very heavy gauge yellow and black cables that attach directly to the terminals of the battery. These are really good and safe to connect your battery to the rest of the electrical system. Okay, I just turned the VEX Cortex microcontroller on. You can see the blinking lights. Now I'm going to turn the VEX game controller on. As you can see, it's flashing a red light right now. Now you see it flashing all green lights after I turn the VEX game controller on. So the order of operations are turn the VEX Cortex on first, then turn on the game controller. Okay, I just powered up the 12 volts power supply. You can hear the two HB25 motors with their fans turning. These fans keep the HB25 motor controllers cool, since they have to control very high currents to the 24 volt Razor motors. Okay, I'm going to power the right motor on. This is the right motor on the my electric car. You can see how fast it moves. Very fast. The motor is right here. Here you see the motor with the small sprocket driving the larger sprocket attached to the wheel. And this is only running at 12 volts, and it's not really yet fully regulated. Even at this speed, it can probably move this car about maybe up to 20 miles an hour, depending on the wheel diameter. The wheels I'm using here are not, they're probably 5 or 6 inch diameter wheels. And it moves backwards when I pull back on the joystick, and it moves forwards when I push forward on the joystick the way it should. So it's totally aligned to direction, moving clockwise when I push the joystick forward, and moving counterclockwise when I push it backwards. This is the left wheel drive. So I'm going to move that one with the left joystick. See, it moves forward clockwise when I push it forward. It moves counterclockwise when I move it back. And it's important to have these two motors moving at relatively the same speed depending on the positions of the joystick. That's called the calibration process. Normally for PID control, that would be incorporated into the control algorithm. PID stands for proportional integral derivative control theory, or control law.